Hey everyone, welcome back to another video of mine where today we're going to be solving Leetcode problem 198 titled House Robber. So we are a professional robber planning to rob houses along a street. Each house has a certain amount of money stashed, and the only constraint stopping us from robbing each of them is that the adjacent houses have security systems connected, and they will automatically contact the police if two adjacent houses were broken into on the same night. So we're given an integer array nums representing the amount of money of each house, and we simply have to return the maximum amount of money that we can actually rob without actually alerting the police, or basically, in other words, without robbing houses that are actually adjacent to each other or next to each other. So in example 1, we have a nums input array of 1, 2, 3, and 1, and basically what these values are basically indicating is that house 0 we can rob $1 from at most, house 1 we can rob $2 from, and so on and so forth up until house 3, or basically the length of a nums input array minus 1, the very last index, or the very last house that we can actually rob from, till the end of the array. So in this case, we would output 4 because the total amount that we can maximum or optimally rob from all of the different possible houses is actually just $4 in this case. Right? We can start off by robbing house 1, which in this case I call house 0, but they call it house 1 in this example, and that's going to be a money of $1. And then we can rob the next house, basically the not adjacent one, but the one after that, which is going to be house 3, which is going to give us a money of $3 net gain, which is going to be a maximum total amount that we can rob is 1 plus 3, which is going to yield $4, which is ultimately the value that we actually output. Of course, an alternate path would be starting at house 0 to get starting at house 1 to get $2, and then going to house 3 to get $1, but that yield a total amount of 2 plus 1, which is 3, which is actually less than 4, and so we'd output the most optimal value here, which in this case is going to be 4. And applying that same logic to examples 2, we have an output of 12 because we can rob house 1, which is going to give us $2, and then 3, and then 5, which is going to give us a total amount that we can actually rob as 2 plus 9 plus 1, which is a maximum value of $12 that we can rob from along the street of non-adjacent houses. So I will give you guys a few seconds to kind of just go over this problem in your and think of a valid solution. And if you guys can't think of a solution, that's completely fine. I will tell you guys how I would optimally solve this problem in a few seconds. Okay, so this is actually a very classic dynamic programming approach, and it has actually a very nice, beautiful solution that I will share with you guys just in a few seconds. So before we actually start with the dynamic programming approach in this solution of this problem, good programming with good practice, we always have to address our edge case or base case handling at the beginning of our code. And in this case, we have two separate base cases for this dynamic programming approach. And the first one is if our nums input array is empty. So basically, in Python, we can get if not nums, or basically there's no elements in nums. Great. We have 0 houses we can rob from, and so the total amount of money that we can actually rob is, of course, $0, because we can't actually rob anything from any houses along the input street, and so we can simply return 0. And our other case is basically if the length of the nums input array, or the street that we're looking at, if that's actually just equal to 1, great, we only have one possible house that we can rob from, and so the most optimal solution, or the most maximum value that we can actually steal from any house is going to be just returning the value at nums at 0, right? We just have to rob from the only singular house that we actually have within our street. And of course, all of these values are going to be hence positive because houses can't have negative amount of money, and so of course we don't actually have to return 0 if it's actually a negative number. We can simply return nums at that 0th index because we're basically guaranteed that they're all positive integers. Okay, after that case, now we actually can start with the dynamic programming approach and initialization of this solution. So first what we want to do is we want to actually initialize our dynamic programming array. And so I'll just short form that to DP, which of course stands for dynamic programming, and that's going to be basically a list of zeros of the length of the numbers. So basically that's going to be a list of 0 times n, or basically n lists of zeros, where n represents the length of the numbers. Okay, and what this basically does is we create a dynamic programming array of the same size of the nums list, initialized with only zeros, and DP at every ith index will basically store the maximum amount of money that we can actually rob up till that house I, or basically up till that house ith index from the previous indexes that we can actually rob from in our nums input array street. So after that, we actually have to have basically our second kind of base case of this initialization of our dynamic programming array, and that's going to be like so. We'll have DP at that 0th index, or basically the very first house that we can potentially rob from, to be initialized to, of course, nums at 0, because they have to match the very first house that we can rob from in the dynamic programming array, has to match the very first house that we can rob from in the nums input array, because that, of course, doesn't have any variations. Now, DP at the first index, or basically the second house that we can rob from, is going to be the maximum value of nums at 0, of the very first house, and of course, nums at 1, the second house that we can potentially rob from. And what this basically does is, for the second house that we can actually rob from, we can either rob house 1, or basically nums at 1, or house 0, or basically nums at 0. And we can basically take and store the maximum of these two values and store it in the very first index of our DP array, and initialize it like so. And after we do this, we can fill in the dynamic programming array for every up till ith index to actually get the maximum value, or the optimal amount of money that we can rob up until the ith index, or basically the length of the nums input array. And we'll just like so. We'll say for I in the range of from the second house till the length of the numbers, because of course we have to actually start from the second index, or the second house of our input array nums, because we already covered the first two houses with our initialization of DP at 0 and DP at 1 to kind of build up from there up until every ith index. Right? And after we do that, we actually have to set DP at every ith index within this for loop iteration of our nums input array to be the maximum value, or basically the most optimal amount of money that we can steal from every house, of DP at I minus 1, the maximum value of that, and of course DP at I minus 2, DP at I minus 2 plus nums at I. And you may be kind of confused. We use the dynamic programming indice, or the DP array, to actually get the indices for these two values, and then you may be confused, why do we use nums at I instead of just DP at I? And the reason we actually do that is, this is actually storing DP at I to be the maximum value of these two values. So we can't actually use DP at I because we wouldn't have actually updated DP at I yet for this in this specific iteration, and of course this would just basically be passed in value of 0. Wouldn't actually change the value of anything, and so we'd actually have to use nums at I before actually updating DP at I. Because in this specific iteration, or basically in this specific max function initialization, this basically sets DP at I to basically be the maximum value of DP at I minus 1, and basically DP at I minus 2. Because DP at I is going to be set, of course, to 0, as in our line 8, and it's not going to be updated until this line of code actually executes, or basically gets finished executing, and so we actually have to use nums at I to actually get the accurate value for that ith house. And to kind of recap, what this actually does is, first we iterate from the third house, or basically I equals 2, or index equals 2, up until the last house, or the length of the nums. Then, what we have to do is, for each house, we have two choices. Either we can skip the current house and take the value from the previous house, which would be DP at I minus 1, or the very previous house of ith indice. Or we can rob the current house and add its value, or nums at I, to the value from the two houses back, basically DP at I minus 2. For example, either we can take 7, if we're looking at 9 right now in the specific iteration of the for loop, we can either take DP at I minus 1, which would be 7, or we can take the maximum value of nums at I, which is 9, and DP at I minus 2, which is 2. And of course, the maximum value of 7 and 9 plus 2 is 11, and so we put that in our dynamic programming array at index I. And same thing for 1, which we also add to our solution, and so we'd output 12 in that visual depiction of what the dynamic programming array actually does. And this will actually just have updated for every single maximum of these two choices at DP at every ith index, and ultimately what we can do once we actually exit this for loop is simply return DP at that last indice, or basically DP at -1 in Python. And this basically what this does is, it says the last element of the DP array, or basically DP at -1, contains the maximum money that we can actually rob from all the houses up until the very last index of our nums input array that's actually completely optimized. And as you can see, it's just about as efficient as you can get. So for an example walkthrough of this problem, let's just consider example 2. Right? Let's just consider nums to be an input array of 2, 7, 9, 3, and 1. First, we'd actually initialize our dynamic programming array to basically be, I'll just type it out, to basically be a list, or basically a list of zeros of length 5. So it'll be 0, 0, 0, 0, 0. Because of course the length of this input array nums is 5, and so we're going to have 5 zeros in one array that we initialize our dynamic programming array to be. After we do that, we set our base cases. So DP at 0, or basically the very initial house that we can rob, is going to be set to 2, right? And so we can update it like this, to 2. And then DP at 1 is going to be the maximum value of 2 and 7, which in this case, of course, is going to be 7, and so we set that equal to 7, and so this would be updated to 7. After that, we actually have to fill in the DP array. And so when I is equal to 2, DP at index 2 is going to be the maximum value of DP at 1, and DP at 0 plus nums at 2, which is going to be the maximum value of 7 and 2 plus 9, which is 11. So basically, DP at 2 is going to be 11. And then for I index I at 3, DP at 3 is going to be the maximum value of DP at 2, or basically DP at 3 minus 1, and DP at 1 plus nums at 3, which is going to be the maximum value of 11, and 7 plus 3, which of course is still 11, and so this would also be 11. And then finally, what we would do is, for I equals 4, DP at 4 is going to be the maximum value of DP at 3, and DP at 2 plus nums at 4, which is the maximum value of 11, and 11 plus 1, which in this case is going to be equal to 12. And so DP at index 4 is going to be equal to 12. And at the end of the day, we can simply return DP at negative 1 once we actually complete that for loop, and that in this case evaluate to 12, which of course is the correct answer, as we saw in example 2 in the walkthrough. So, like I said, at the end, the DP array would be 2, 7, 11, 11, 12, just like we talked about right here. And so the maximum amount of money that we can actually rob that's actually optimal is going to be $12, or basically whatever unit that Leetcode prefers in this problem. So that's dynamic programming for you in a nutshell, basically a very classic problem of this algorithm. And if you guys enjoyed this and learned something new, please consider liking this video and subscribing to my channel. It really does mean a lot. And without further ado, I will see you guys in the next video. Bye-bye.